Hello AP Physics students, this is Mr. Kennedy. Welcome to your first video lesson, the first video lesson I've ever done too. We're going to talk about magnetism here today. And in the style of kind of V-Heart, we're going to use this little whiteboard to give you some ideas about some magnetism with particles today. So the first thing is we've already talked about the fact that the force on a wire was F equals BIL sine of theta. And that's when you have charges flowing through a wire that you get this force that acts on a wire. But the reality is it's not the wire that causes the issue, it's the charges inside. So when you look at it, the force is really due to, that's B, the current is charge over change in time, and we have this. But if you look right here, L over T, well, that's velocity. So what you get is F equals BQV sine of theta. Now, if you want to get really technical about this, this is really a cross product. Just like we did with the F equals BIL equation, for this equation, it's really going to be the force is equal to QV cross B. So because it's a cross product, that means we're going to have the right-hand rule. But the right-hand rule is the exact same right-hand rule that we use for the wire. The only weird thing we have to pay attention to is whether you have negative charges. So let's take a look at a little example here with some charges going into a magnetic field, and we'll see that the right-hand rule is almost exactly the same. So if we have a magnetic field here pointing into the page, right into the board down there, and then we have a positive charge here that's projected into the magnetic field. Well, because we consider currents to be positive when they go in, we take a look at the right-hand rule, and what we say is that if we take our right hand, the magnetic field points into the page, the thumb points in the way a positive charge will move, so that's in this case to the right. So therefore, the magnetic force on this particle, once it gets in the magnetic field, will be upward. It'll start to move up. But then, because the particle is moving upward, we can point our fingers into the page, thumb up because now the particle is moving up, and now it'll be pushed back to the left. So now it does this. Now that it's coming back to the left, now the particle is moving to the left, fingers are into the page, now it pushes back down. And what we get out of this is a nice circular pattern. And you'll see this in some particle accelerator pictures as well. You have particles that once they go inside the magnetic field, they'll spin. In fact, that's why Fermilab is, it's Tevatron, which was shut down now, but that's why it was one giant ring, is because you would have particles moving in a circle. Now the only problem is when you have negative particles, let's say you have a negative particle that's going into the magnetic field, the only difference with this right-hand rule, it's still fingers are magnetic field, thumb is your current, and palm is your force, just like with the wire and just like with the positive charge, but now you have to make your right hand with your thumb pointing against the way the charge moves, because we look at the way positive charges move. So with negative charges, we point our thumb the opposite way. So fingers are into the board, thumb this way. So now what you see is that will make the particle move down. Now from there, we take our thumb, point it against it as well, and fingers in like this, and now the particle moves back this direction toward the left. Now we see the particle is going to move up, and we complete the circular pattern again. This particle will move into a circular pattern. If the particle was neutral, because there's no magnetic forces on neutral charges, in fact, I'm going to refer you to a video in the next couple of days about why moving charges have magnetic fields. This particle would just go straight through undeflected. Nothing's going to happen because it's not charged, so it won't be affected by the magnetic field. So again, positive charges, point your thumb in the same direction as the charge. Negative charges, point your thumb in the opposite direction as the charge, and then you'll be all set. But what you'll see here is in each one of these circumstances where you have a particle moving into a circle, the force diagram on it is just one force. This force is the magnetic force. because that magnetic force is the only force acting on it, it must be the centripetal force. And if it's the centripetal force, then we can do something, we can find something out about it. Because if the centripetal force is equal to the magnetic force, that's magnetic force, then mv squared over r, the centripetal force, will equal bvq. I'm not worried about the sine of theta here because the sine of theta is just the sine of 90, so that's just 1. And we see some things cancel. The v cancels right there. And what I'm left with if I rearrange is that the radius this particle will move in is mv over bq. And this is a very, very common thing that'll show up in the AP test or in other problems. But again, even in particle physics, one of the ways to take a look at what a particle is to see what happens when it interacts with the magnetic field, and you'll see what kind of radius it makes. And then you can actually help determine what that particle is from there. So the basic lesson for today is that we saw that the magnetic force on a particle was bvq sine of theta. We have to use the right-hand rule. This time the right-hand rule will be with fingers in the direction of the magnetic field, thumb in the direction of the current, meaning that the way the positive charge moves, you got to be careful with negative charges, and then palm is still the force. And those particles will very often move in circular patterns. So now it's time for you to go ahead, do some practice problems with that. I've left worksheet 2 from unit 12, problems 1 through 5. Be careful with problem number 5. It's a little bit more challenging. And then I will see you back tomorrow for the next lesson. All right. Have a great Tuesday, everybody.